Hello everyone, this is lecture 6 of course BE544. In today's lecture, we are going to continue the journey with handling the whole slide image annotations and extract different tiles from the different regions for different classes such as benign and sarcoma. But first, let's recap the previous lecture. In the previous lecture, we have read the whole slide image, read the different annotations, and these annotations belong to three classes: benign, sarcoma in situ, and sarcoma invasive. And we understood the differences between them and also the normal class. Then we have combined and masked the annotations with the whole slide image, and we were able to highlight the different annotations using Python. Then we focused on extracting a region such as this region, and based on the annotations we applied a masking so we could extract the region of interest as we saw here. We were also able to visualize different regions from different levels, and in this dataset we have 3 levels. Some datasets can contain multiple levels such as 4 or 5 levels depending on the magnifications. So in this lecture we need to extract the different regions, especially talking we need to extract patches and tiles from different levels, and these levels should be corresponding to each other. So for example, if we need to capture and extract a region with a size 512 by 512 from level 0 as shown here, for example for the first region, so we cut a 512 by 512 tile in that level, which is reflected here. So if we zoomed out, fixing the XY coordinates, which are here and here and here, so we can get a zoomed out version that contain the same shape with other details. For example, for level 1, which is a magnification by 4, we can see that the tile we extracted in level 0 appears here, and for level 2 the tile appears here. What's happening now, we are fixing the XY coordinates and we are trying to extract the same width and same height from the different levels, and each level has a specific magnification level. So when we zoom out, we get less details for a specific tile, but we are getting some other tiles together, such as here, here, and here. What's happening now is mentioned earlier, pyramidal view. So in pyramidal view, we are dealing with something like a cone or a cylinder. So assume you are getting a region with XY coordinates here and width and the height, and you are trying to get the corresponding ones in other levels with the same width and the height, so you can get this one and that one. But if you focused on the region that you need in level 0, you can find that region is zoomed out and appears in a small size like a cone. So if you visualize that here, so this is the base of the cone and this is the top of the cone, like that. And as we see here, in level 0 appears like that, in level 1 appears like that, and in level 2 appears like that. The advantage of getting a cone or a cylinder in the different levels that we can apply each level to a specific classifier, and then we can obtain the decision from each level, and then we can combine them together and apply majority voting or apply another classifier, as we saw in the third workflow in the previous lecture. But there is an issue with that approach in some projects and datasets, that for level 0 and level 1, for example, when we zoomed out, we were able to get the neighboring features and the neighboring tiles in that direction and in that direction, but we weren't able to get them in that direction and that direction. And based on what classifier or what model we are dealing with, such as CNN or Vision Transformer, we need to get the neighboring tiles so the model can get a vision on what's happening around the tile and what features can be extracted from the surrounding. This issue can be solved by not fixing the XY coordinates. As mentioned from a while, we are fixing the XY coordinates for the 3 levels. So basically, we can change the XY coordinates for each level so that the tile can be centered. And this approach can be converted to that. Simply, we need to make a symmetric cone or a symmetric cylinder. So if you are extracting a tile like that, we can simply play with the XY coordinates so that the tile in the demagnified level, such as level 1 and level 2, appears in the center, like here and like here. And based on that, the model or the tile can contain the features in the 4 directions. So we have now at level 0, this is the base, and once we get in the higher levels, we represent a cone, but that cone in that case is symmetric. So the distance here is similar to here, and the distance here should be similar to here. These two approaches can be used in different applications. The first by fixing XY coordinates, and this approach is easy to implement. And the second approach to make it like a centered cone, where we can get the different tiles that surrounds the target tile. Simply to do that, we can play with the XY coordinates as mentioned. So assume this is level 0 and this is level 1, and the magnification level is 2 between these two levels. So each 2 pixels here will demagnified to 1 pixel. So this is 8 by 8 divided by 2. It will be converted in level 1 to 4 by 4, like what we see here. So simply we have now XY coordinates here and XY coordinates here, and assume this grid represents level 1. So if we shifted that grid from this position towards that direction, we can center the tile in level 1 as here. So you are now, instead of extracting at XY coordinates, we are extracting it at X bar, Y bar coordinates. So what's given is the XY coordinates, and based on the downsampling or the demagnification level between level 0 and level 1 or any 2 levels, we can obtain X bar and Y bar coordinates. How to do that? We need to extract the X coordinate by a specific size so we can get X bar, and we need to subtract Y by another specific distance to get Y bar. How to get this distance in the X and Y coordinates? Simply, we have the whole width of the tile, which is for example 512, that we need to extract. So we simply split it in 2 portions so we can get the size of half of the tile, which will be for example 256. And then to get that small distance, we can get also the half width of the tile and subtract the half width of the whole tile by the half width of the small tile, so we can get this small distance. So to get the purple region, we divide width by 2, and to get the blue region, we simply divide the width by 2 multiplied by the downsampling factor. If we extracted width by 2, we can simply width by 2 here will get 1, and width by 2 here will get 1 over d. So the factor that can be subtracted from the X coordinates will be width over 2 multiplied by 1 minus 1 over d. And d here is downsampling ratio from level 0 to level 1 or from level 0 to level 2. By getting that factor, we can subtract x from the factor and we can get X bar. The same for Y and Y bar, but we will change the width to be the height. So if you applied that on our example, the factor will be width over 2, which is 8 over 2 will be 4 multiplied by 1 minus 1 over d. And as we said, the magnification is 2x, so 1 over 2 will be half. So 4 multiplied by half will be 2, so the factor will be 2. So if x is here, we need to get the direction with 2 squares, and the same applies for the height. Another example, assume you have a magnification level or downsampling factor of 4 with a width of 16 and x equals to 6. What is the x bar, which is visualized here? So simply by applying the same equation, width over 2 multiplied by 1 minus 1 over d, will get 16 over 2 equals to 8 minus 1 minus 1 over d, 1 minus 1 over 4. This will get 6. So x bar will be x minus 6 equals to 0. So to move from x to get x bar, we move 6 pixels or 6 squares in that example. 1, 2, 3, 4, 5, 6. So x bar will be here. By applying the same for y, we can get x bar and y bar. That will be that point. So instead of cutting a tile at xy coordinates to get that whole region in the gray shadow, we simply cut from x bar and y bar coordinates so we can get that region. And if you notice, in the first one, the tile or the small tile appears in the top left corner, but by shifting in the direction, the small tile will be centered. To be more generic, assume you need to map from any level with a magnification d bar to any level with a magnification or downsampling d. So the equation or the factor equation will change from 1 over d to be 1 over d over d bar, because this equation applies from converting from level 0 to any level. But to be more generic, assume we need to convert from level 2 to level 3. So you simply divide the 2 downsampling to get only the portion which is demagnified by dividing d over d bar, and then we can get the factor. And it's worth noting that OpenSlide requires any dimensions to be in level 0. So after we calculate the factor, we need to multiply it by d over d bar before performing the subtraction and applying it to the read region function in Python. So mathematically, this equations applies, but in Python, using the OpenSlide library, we need to modify the factor so it can be coordinates in level 0, as OpenSlide package understand the coordinates in that level. So let's go ahead and apply that code. And in that code, we need to get a tile in any region and the centered view at level 1 and level 2. And we need to validate that by visualization. So we first imported, as we did in the previous lectures, the DLLs, and then imported package of OpenSlide, Matplotlib, and NumPy. Then we defined the SVS file or the whole slide and specified the slide object by passing the file to the OpenSlide class. And then we defined XY coordinates where we need to extract the tile at level 0 with a width and height of 512 by 512. Then we looped on each level, and in each level we need to extract the tile. So we simply applied the same ratio or factor that we saw in the slide. So first we calculated d over d bar. So we divided the downsampling property of the eye level, which starts from 0, 1, and 2, by the downsampling factor of level 0, as all dimensions will refer to that level. And based on the ratio, we applied the factor for the width and height by simply multiplying width over 2 by 1 minus 1 over the calculated ratio, and then we convert it to integer, as the dimension should be in integers. We did the same for the height, and based on that, we subtracted each from x and y, which are the original coordinates, But first, as we mentioned, we need to multiply by the D ratio so OpenSlide or the function read region can understand it. By doing that, we can get the centered region for each level, and we here visualized each tile by converting that extracted region to RGB color first and then to NumPy array, and then we visualized the tile. And to verify that we got the correct centered tile, we simply grouped that region and visualized it so we can by eyes say what we did is correct or not. Before understanding what's happening here, let's run the code and get that idea. As you see here, in the top row, we have the tile for each level, and for level 0, it will be the same for the grouped, but for level 1, we needed to get that small region and visualize it to be in the lower row, like here, and by eyes, we can say that level 0 is similar to level 1, but in a demagnified version, because the more you go higher in the magnifications or in the pyramidal view, you will get less or less fine details. The same for level 2. If we grouped that very small region, it will look like that. And for level 2, level 1, level 0, they refer to the same tile but in different magnification levels. How did we do that? As I made with my arrow here, we needed only to extract that small region which is in the center. If you are able to get the boundaries for that tile, we can simply group it from the whole image and visualize it. So simply, we started from the factor height, which is the shift happened to the top, and cut it a portion of the height divided by the ratio. What does it mean? As we mentioned in that slide, we said we need to go to the top by a factor and go to the left by a factor. So if we started to group the image from that factor and got the height, but after demagnification, we can simply group that region. To get the demagnified size, we simply divide the size by the downsampling factor, as we did here. So we extracted from the calculated factor, which is that portion, to the height over D ratio. So if the height is 16, for example, over 4, it will be 4. As we see here, the height is 4. The grouping in NumPy requires the starting and ending boundaries. So the starting boundary will be the factor, and the ending boundary will be the factor plus that calculated ratio. So the factor to the factor plus the calculated ratio. So by doing that for the height and width, we can get that small tile in the center. And also we have 6 figures because we have 3 levels, 3 in the top, 3 in the bottom. So we here defined two rows with columns of slide levels. So if we have 3 levels, we will get 2 by 3 grid in Matplotlib. And we defined here the tile should be presented in the top row and here in the bottom row. How did we do that? Here we set the counter that starts from 1. So that one should be 1, 2, 3, 4, 5, and 6. And to access that one or the figures or subplots in the bottom row, we simply add 3 here. So in the first level, the tile is added, which is that one, and by adding 3 to get the grouped version, it will bypass this one and this one currently and add that subplot. And in the second iteration, it will add for level 1 here and the grouped version, and the other iteration will add that one and that one. Finally, after completing the loop, we presented and displayed the visualization. So in that code, we applied the factor we have determined and visualized it and verified it using eyes or visualization. Next, we need to apply the annotations or the masks with the regions. so we can extract only the tiles which is related to a specific category. So we have understood how to get the tiles. So now let's move how to handle the masks so it can be corresponding to the demagnified version of the tiles in the different levels. If we applied the same mask for level 0, level 1 and level 2, it will be wrong. Why? Because we are doing two things. First, we are demagnifying, so the target tile for a specific category will be less in size. Second, we are centering the tile to the center in the different levels, so we need to do two things for the masks. First, we need to decrease the size of the mask and then shift it to the center as we did with the tiles. So first, to map the annotations mask from a level D bar to another D, and D here represents the downsampling, for example 2x or 4x, divide by D over D bar. So as you see in that figure, the height is about 3k in level 1 divided by 4, in level 2 divided by 16. Then, after resizing the levels of the masks, we need to center it or push it to the center. So simply to do that, we will apply padding to the mask to be in the center by the same calculated factor, and also we will need to update the shifts. How to do that in the code? First, we imported the DLL and the different packages, and we added here XML package to read the annotations. Then we created two functions, one to extract annotations and another to extract the mask, and these two functions include similar script of the previous lecture as we are going to see now. And then we defined the two files, created the object, defined the width and the height, and currently we defined the index of the annotations that we need to deal with. But generally we need to loop on all of the annotations as we are going to see in the following scripts. So we applied the D ratio and calculated the factors. Then we extracted the annotations from the XML file, and for the annotation list we extracted a specific region and got the coordinates, and from these coordinates we extracted the mask. Then for the mask we got the region mask as we did in the previous lecture. So let's go to the implementation of these two functions. First, we go to extract annotations function. In that function we simply did the same code of the code we did here by parsing the tree and the different vertices, and we got XY axis, which are the coordinates. But the small modification we applied here, we divided each X and each Y by the D factor, as we mentioned in that step. Now we have the different annotations in the whole slide image based on the XML file. So let's go to the other function, which extract mask. We define the coordinates of a specific annotation, and based on that we extract a mask as we did in this code from the previous lecture. And the small modification we applied here, we wanted to get the padding from the different directions, so the mask can be look like that for level 1 and like that for level 2. So to pad the masks, we simply need to get the remaining width and remaining height, and based on these two values we split the remaining width into two halves, one in the left, one in the right, and the same for the remaining height, one in the top and one in the bottom. And then we can use copy make border function in OpenCV package to define what do we need to pad, define the borders, top, bottom, left, right, and we tell this function to apply a constant border with a value of 0 around the mask. So how do we calculate the remaining width and remaining height? Simply, in the rule here, pad the mask to be in the center by the factor D by D bar. So we have a width, we multiply it by d by d bar and subtract it from the original width so we can get the remaining distance. This is, for example, 1200 in width, so by applying demagnification to the second level, this region should be divided by 4, so the width of that region will be 300. So how to get the remaining distance? So simply multiply that value by the d factor, which is d over d bar, to get the original 1200 and then subtract it from the 300 so we can get the distance here plus the distance here, which should be 900. Then we said to update the shifts. So instead of handling at xy coordinates to be 0 and 0, we need to handle it at z coordinates. So we added for each x and y in the shifted coordinates, added the remaining widths over 2. So if you said we need to add a padding here and here with 900, we simply shift all x's with this distance, which is 900 over 2, which is the remaining distance over 2, which should be 450. Then we returned all variables so we can use it later. So that function extracts the mask, demagnifies it, extracted the mask, pad it and apply the shifts, and then returns the modified masks and coordinates. Now we have the mask. We need to get the region so we can apply bitwise AND between both of them so we can get the region of interest. So for the region, to get the xy coordinates, we simply got the top left corner and multiplied it by the magnification level, and then applied the same formulas similar to the previous code and extracted the region and converted it to RGB. And the same we did for the mask, and we cropped the region mask, and then based on the region mask and the region slide, we applied bitwise AND between both of them to get the region of interest. And as we said, we have in the region of interest 4 channels. We need to convert it to RGB, so applied convert color function from the OpenCV package. Then we visualized the region slide, the region mask, and ROI, which is the region of interest. We have 3 levels, 3 plots each in each level, so we will get 9 subplots. If we executed the code, it should look like that. We have level 0, a specific tile with a width and a height. We got the mask with the same width and the height, and then we applied bitwise AND. And for the second level, if you see here, that region can appear in the center. We did the same for the mask by demagnifying or downsampling it to a smaller size and applying padding. Then we applied bitwise AND between the mask and region slide to get the ROI, and the same we applied for level 2. Next, we need to extract region tiles with overlapping. In the previous code, we have extracted a region at specific coordinates, which were the top left corners of the annotation, but now we need to extract the different tiles from the extracted region. So assume that tile which is extracted is 1K in width and 2K in height, and we are extracting small tiles with specific widths of 500 and specific height of 500. Then we need to get 8 tiles. So the concept of overlapping here is, do we need to let the model understand local and global features from different tiles and relearning again on other tiles with a small portion of the previous or other tiles or not? This is the concept of overlapping. So in overlapping, if we didn't apply it, we simply crop the tile at a specific width and height. Then we go to the following tile and other tile and so on for the others. And in that case, that new tile has no information of the previous tile. But by applying overlapping, the tile will get a percentage of information from its previous tile. So for example, if we need to apply 50% overlapping, then this tile, which is in navy color, will get 50% of information from the previous tile, which is in green color. This will increase the number of extracted tiles and also can increase the ability for the model to get a relationship between the different tiles and understand that this tile has some neighbors like that from the left, from the right, from the top, from the bottom, and so on. The choice of overlapping percentage depends on the application and on the objective of it, and also on the dataset. So for example, if we have a dataset with a small size and small number of samples or records, so we can simply increase the number of overlapping so we can get more tiles to be applied to the model to learn. And also you can make that percentage as a tunable hyperparameter by trying, if you applied 25%, 50%, 75%, and so on, which can get the highest performance and stick with it. So how can we apply that? Simply, similar to the previous code, we have the two functions. We have the same structure of the code, but instead of specifying a specific x and y coordinates to work with here and for the mask, we simply applied two loops because we are in 2D. Here we defined the width and the height, the annotation index, as we did in the previous code, and here we applied the percentage of overlapping, which is 50. How did you know that? Because we are specifying here 256 and the width is 512. And if we change that to 128, the percentage will be 25. And here we define the parameter that we are going to discuss after a bit is tolerance with a value of 0.7. So here we took the previous code and applied two for loops, and simply for the x and y for the masks, we added x for x mask and y for y mask, so it can get the next tile by moving to the right and moving to the bottom. We did the same for the region by adding x here and y here, and we followed the same structure for the code, but we added two conditions. First, if you are going to extract a mask which is not equal to the same specified size, ignore it. So if you focused here, you can see that there's some region remaining at the end which is not equal to the same width and height, so we can ignore it. And we need to check the percentage of the mask. What does it mean? If you remember, the mask can look like something like that. So if you are going to extract a region here and applied the corresponding mask, it will get an ROI. But if you got a region here and applied a mask, which in that case will be an empty mask or zeros, you will get no ROI. So this image will be extracted as a black image, which is useless. So we need to get how many non-zeros pixels, the summation of it or the percentage of it, and check if you need to take it or not based on a threshold or tolerance. So for example, if we are going to extract a region at specific at this direction, at this coordinates, so this region will be filled with ROI, but that region will be in black. If we calculated the percentage, we can say take it or not. The percentage of what? What is the summation of non-zero pixels? And compare it to the total size multiplied by the tolerance. And here we divided the tolerance by the D ratio squared, because when we get from a level to a higher level, the mask will be downsampled in the width and the height. So we divided the tolerance, a D ratio for the width and a D ratio for the height, because we are dealing with 2D, so we squared that number. Based on these two conditions, we can get refined ROIs. After that, instead of visualizing the ROIs, masks, and regions, we simply exported them and wrote them as images. We exported the masks, we exported the tiles, which are the regions, and we exported the ROIs, each in a specific folder. So if you executed the code, it will loop on the specified annotation index and loop from the top left corner with a specific width and height and overlapping of 256 in width and height, and applies the loop and extracts the three things: mask, ROI, and tile. If you went to the folder after executing it, you will find the output, as we see here, with the different levels. And because the first one is benign, all were postfixed with the benign keyword or category. For example, if you opened the ROIs for level 0, which is here, and if you opened the ROIs for level 1, like here, and for level 2, like here. And depending on what you are doing and what tolerance in your application and different specifications on the objectives, you can simply post-refine the ROIs, because you can say, I don't need that region or that region. You can simply delete them manually. So now we are able to extract the tiles with the corresponding masks and ROIs at a specific annotation index. This is the applied example. This is another example. This belongs to Sarcoma and Cyto, as we see here in the image scope. This is for level 0. When demagnified appears here, when demagnified appears here, and based on the masks, these are the different ROIs. So what we did is related to a specific index of annotation. What about if you need to extract all of the annotations in the whole slide image? We simply use the same code, but in that phase we will apply another loop to loop on all of the annotations in the whole slide image. So the change here appears in that portion. After getting the annotations, instead of getting a specific mask similar to what we did in the previous code, we simply applied a for loop to loop on all of the annotations or a specific number of annotations. Here we are specifying 5 or the first 5 annotations, but if you need to get all of the annotations, we replace the 5 with the length of annotation list. Then we extract the region tiles, and we encapsulated the code we did here in a function to make the code organized. So in that extract region tiles function, here we got the coordinates, mask, and made the overlapping, and then got the region, the ROI, and exported the images. So if you apply the code, it will start, and it may take time depending on the annotations and the size of the tiles and the overlapping percentage. But finally it will get you the 3 levels with the 3 categories: benign, Sarcoma and Cyto, Sarcoma invasive, for all of the annotations in that whole slide image. So what we did in this lecture, we were able to apply pyramidal level with a specific tile and center it, so we can make it a symmetric tile so that we can get features from the neighbors from different directions. Then we applied the same for the mask. We were able to extract tiles with overlapping from a specific annotations. Then we upgraded the code to extract all of the annotations in a specific whole slide image at the 3 levels or the different magnification levels. But the question now, we were able to extract the 3 categories, but we mentioned in the dataset specifications, we said we have 4 classes: normal, benign, Sarcoma and Cyto, and Sarcoma invasive. We were only able to extract benign, Sarcoma and Cyto, and Sarcoma invasive. But what about the normal class? So the bonus question for this lecture: how can we extract the remaining part of the whole slide that corresponding to the normal category so we can get the 4 classes? If you have an idea, you can submit it in the following assignment, and you can get bonus of 100 points added to the assignment section, and the solution must be implemented and working.